Today we're going to look at fluid statics and fluid dynamics. Fluid statics is when the fluid is not moving. When we were dealing with rigid bodies, then we could assume that forces acted at points. We could push things around with a needle if we needed to. We didn't have to worry about anything else. But if we're looking at fluids, we have to apply the force over an area. And a force over an area is a pressure. So our units are going to be newtons per square meter, and that's also known as a Pascal. Density is another thing that we're going to need. That's mass divided by volume. Notice that this is a capital P and this is a lowercase Greek rho. Density units there are kilograms per meter cubed, and for comparison, water is 1,000 kilograms per cubic meter, air is about 1.3, aluminum is about 2,700, iron 7,800, mercury 13,600 is the densest liquid, and lead, which we think of as dense, is actually slightly less dense than mercury. There are two different kinds of pressure that you typically see people talk about. One of them is absolute pressure, which is an absolute measure of the force per area on a surface. And then there's gauge pressure, which is what you would get from something like a tire pressure gauge. And the difference in that is atmospheric pressure. For example, if you have a tire that's ripped completely apart and is not holding any air, if you put a tire pressure gauge on it, it'll read 0, but that doesn't mean it's a perfect vacuum. It means it's the same as atmospheric pressure. So we can say absolute pressure is gauge pressure plus atmospheric pressure. We use a little 0 for that. Now, in reality, there's no such thing as a single atmospheric pressure, since it changes all over the Earth, and depending on the weather and changes with the altitude. We typically associate high pressure with nice weather and storms with low pressure. We're going to ignore all that and just set P0 equal to a constant value of 101,300 pascals everywhere. Also, some of the stuff that we're going to be talking about when we talk about fluids, some of it only applies to liquids, and some of it actually applies to gases as well. So I'll try and let you know what the situation is for each item that we come across. Okay, what's the source of atmospheric pressure? It comes from the weight of all the air around us pushing down on us all the time. So we could say, what happens if we go inside? Now, instead of having miles of air above your head, you may have a meter or two of air above your head. And if we take a 1 square meter table, which is very small, it's a little larger than a nightstand maybe, that's apparently supporting 100,000 newtons, which is over 20,000 pounds. How is that cheap table holding up 22,000 pounds? The answer is that pressure is transmitted uniformly and undiminished through a fluid, and here we mean gas or liquid. The undiminished part means it doesn't matter if you come inside. That's not going to remove the rest of the pressure overhead, and the reason is the pressure goes in all directions. That's the uniform part. So the table itself is not holding up 20,000 pounds because although there's 20,000 pounds pushing down on it from above, if you go underneath the table, there's pretty much 20,000 pounds pushing up on it from below. So that's the reason we don't really have to worry about atmospheric pressure in general. Now for a liquid fluid, there's a pretty simple connection between pressure and depth. We can imagine this column of fluid and it has a height h, and we give it a square cross section. So this could be an oddly shaped aquarium tank or something. And we say the square has a side length of s. The total weight of this column on the floor is the density times the volume, which is the mass, times gravity. The volume is the same thing in this case as h times s squared. So we could say the weight is rho g h s squared. Now the pressure on the floor is that weight, which is a force, divided by the area, which is s squared. So we could say the pressure is rho g h. Now, the thing we can't ignore, though, is the fact that the atmospheric pressure is still present because, remember, it's transmitted undiminished through the fluid. Going underwater won't let you hide from atmospheric pressure. So our general formula is pressure at the bottom of a column of water is atmospheric pressure plus rho gh. How tall of a column would we have to have for its pressure to be equal to the air pressure by itself so that our absolute pressure is twice the air pressure? This is pretty easy math to do. We can set our total pressure to 2 atmospheres and then plug this in, and we see that we get about 10.34 meters. And that's the height of a column of water with the same weight as a column of the atmosphere of the Earth. There's a couple of ideas we get out of this. For example, if you've used a water cooler, pet feeder, something like that, you might have noticed that for at least some of them, you have a big bottle and you flip it upside down into a little saucer that holds water. There's not a valve or anything like that that catches it. And you might wonder, why doesn't this run right out and fill up the floor? And the reason is the atmosphere is pushing down on that surface right here with a force that's enough to lift up 10.3 meters of water in this bowl. Now, of course, if you had a 12-meter tall pet feeder, which I've never seen, water would run out of it to a height of about, the height is only about 10.3 meters because the atmosphere can't hold up an infinitely tall column of water. What this also means is if we had a very long straw, say 100 meters, you're at the top of a tall building and you have a drink down the sidewalk, if you could generate enough of a vacuum, could you drink your drink from the top of the building? And you can't, because you could have a perfect vacuum on top of the building and the height of the water in the straw would top out at 10.34 meters because the vacuum isn't really what's doing the work, it's the air pressure pushing down on it. Now, since we know that there's a connection between atmospheric pressure and the weather, people got the idea a long time ago that we could use that height of a column of fluid to measure this pressure and predict the weather. Now, the records recorded on the Earth, the lowest atmospheric pressure at sea level was about 8.87 meters of water, and the record high is about 11.1 meters of water. So this would be a very large test tube full of water, 35 feet more or less. What we could do to make it less unwieldy is we could use a much denser liquid, like mercury, for example. There, since it's 13.6 times as dense as water, the height will be 1 over 13.6 multiplied by that 10.34 meters, or about 760 millimeters. And some chemists still use 760 millimeters of mercury, Hg, as the expression for atmospheric pressure. And blood pressure is commonly measured in millimeters of mercury as well. The reason this works for liquids and not for gases is it assumes that the liquid is incompressible, and that's actually an excellent approximation for liquids, but it's horrible for gases. If you go from the surface of the ocean to the deepest part of the ocean, where you have a column of water kilometers tall pushing down on the water at the bottom, the seawater's density will only go up by 2 or 3%. So we're going to consider all liquids to be completely incompressible, and that way density is independent of pressure and it's a constant. There are also some changes in density due to temperature. We're going to